Okay, our next speaker is Liang. He will present the paper, Data Can Speak for Itself, Quality-Guided Utilization of Wireless Synthetic Data. Liang is the third year's PhD student candidate at Peking University. His research interests include wireless data collection, data generation, and their practical applications. Please join me in welcome Bo for presenting their work.
Good morning, everyone. My name is Liang, and I'm a third-year PhD student at Peking University. I'm here on behalf of our first author, Chen, who was unfortunately unable to be here due to visa issue. Today, I'll be glad to share our work on the quality of wireless synthetic data. This research was a joint effort with my supervisor, Professor Chenren and our collaborator, Professor Wei Gao from the University of Pittsburgh. Thanks for all great authors. Wireless sensing has enabled a wide range of applications in our daily lives, including indoor localization, human activity recognition, liquid classification, and more. In the area of deep learning-driven wireless sensing, these applications have become increasingly data-hungry. Traditionally, researchers collect data manually, which is both labor-intensive and time-consuming. Fortunately, the recent rise of generative models has become a turning point. Wireless researchers can now use models such as GANs and diffusion models to generate synthetic data. The synthetic data can complement real-world data and accelerate the development of wireless sensing applications. Next, I'll give a brief overview of how current wireless generative models work. First, a generative model is trained using real-world wireless data along with corresponding labels. These labels are worked as the conditions, such as user identities, locations, and action types. Once trained, the model can generate new synthetic data by taking specific conditions as input. These conditions also serve as labels. The resulting data label pairs can then be used to train downstream models. For example, an action recognition model with improved accuracy. So condition-controlled generation of labeled synthetic data can increase data quality. But what about the data quality? In our paper, we take the first step towards evaluating the quality of wireless synthetic data, and we focus on two key attributes. The first one is affinity, which measures the consistency between real and synthetic data. For example, if you input the condition running, the generative model should produce a signal corresponding to running, not different actions like stretching. The second attribute is diversity. A model might learn to always replicate the same patterns from the training data set. While this may lead to high affinity, it's not what we want. Instead, we expect the generative model to produce diverse data that introduce useful variations to improve task performance. While these two attributes are easy to understand, they are very difficult to measure directly because it's hard for human or physical rules to accurately explain wireless signals. For instance, when looking at raw Wi-Fi CSI signals, we cannot easily tell which action they represent or whether they are diverse or consistent. This leads to our insight for quality assessment. Instead of evaluating data at signal level, we use task models to assess the quality because the ultimate goal of synthetic data is to improve task performance. We call this task-oriented quality assessment. When we talk about task models, we can train them in two different ways. The first type is trained on real data and tested on synthetic data. We refer to this as TR, short for train real. We will show later that TR accuracy reflects the affinity of synthetic data in how well it aligns to the real distribution. The second type is the reverse. We train the model on synthetic data and test it on real data. This is called TS, or train synthetic. TS accuracy captures the diversity of synthetic data in its ability to generalize and support real-world task performance. So why do these two types of task models reflect the affinity and the diversity of synthetic data? Let me explain using a classification task as an example. This is the first example. We train the task model using synthetic data and evaluate by real data. The pink rectangles and triangles represent two classes of real data. Suppose we generate synthetic data that has high affinity but low diversity, represented by the brown rectangles and triangles. If we train a classifier on these synthetic data, the resulting decision boundary will look like the brown line. As you can see, a few real simples fall on the wrong side of the boundary and are misclassified, leading to a low TS accuracy of 4/6. This happens because the synthetic data doesn't sufficiently cover the full range of real data variations. As a result, the model trained on it performs poorly on real data, leading to low TS accuracy, which indicates a lack of diversity. In the second scenarios, we do the opposite. We train the model using real data and evaluate on synthetic data. The decision boundary is now determined by the real data. If the synthetic data lacks affinity, even if it shows some diversities, many synthetic simples will fall on the wrong side of the boundary and be misclassified, leading to a low TR accuracy of 3/5. This suggests that the synthetic data does not match the intended distributions, and it may contain misleading simples. The low TR accuracy reflects poor affinity. In the last example, we show synthetic data with both high affinity and high diversity. The task model trained on real data can accurately classify synthetic data, and the model trained on synthetic data can accurately classify real data. The high TR and the TS accuracy reflects high affinity and high diversity. To summarize, you can think of TR as a way to test how well the synthetic data matches reality, and the TS as a way to test how well synthetic data supports reality. Our task-oriented assessment goes a step further. The most straightforward performance indicator of the two types of task models is accuracy. However, a single number like accuracy doesn't tell the whole story. It gives us limited insight and makes it very difficult to compare performance fairly across different data sets. So instead of accuracy, we propose using the margin distribution. The margin of a simple is the difference between the model's confidence in the label class and its confidence in the next most likely class. For example, for this simple corresponding to running, the model prediction probability of its label is 0.7, and the largest probability except the label class is 0.2. We calculate the margin 0.7 minus 0.2 equals 0.5. A correctly classified simple will have positive margin, while a misclassified simple will have negative margin. The margin calculation of other simples follow the same methods. By calculating the margin for every simple in our testing set, we can create a cumulative distribution. This distribution provides a much richer picture of the model's performance than a single accuracy score. So how does this enable a fair comparison? Here is the key insight. For any data set, the best we can expect the model to perform is how it performs on the data it was trained on. Therefore, the margin distribution on the training set acts as the perfect reference or a golden standard for what is achievable on the specific data set. The quality of our synthetic data can then be measured by how closely the test set's margin distribution matches this ideal reference distribution. The closer the match, the better the synthetic data quality. This page summarizes existing wireless generative models. We categorize the synthetic data according to source and target domains. Here, the domain refers to application-specific aspects, such as human hardware setups or time variations. In the cross-domain setup, the models transfer real data from the source domain to the target domain. In the in-domain setup, the models generate additional data within the same domain. We select one representative work from each type, CSI GAN and RF diffusion, to evaluate the corresponding synthetic data quality with our proposed framework. The evaluation results are shown in the figures. For affinity, we observe a clear gap between the test and the training margins, as highlighted by the red arrow. This indicates a problem. Real and synthetic data don't align well. For diversity, the region marked by the rectangles shows that the margin distribution have similar shapes. This suggests that the synthetic data capture a wide range of variations. In short, today's wireless synthetic data shows good diversity, but still suffers from limited affinity. Our next research question is the cause of limited affinity in current wireless synthetic data. We identify reasons before and post-generation. When the training of generative models have incomplete class coverage, the untrained classes transfer badly, resulting in low affinity data. Secondly, problems may arise from application-specific data transformations. For example, in Wi-Fi sensing, raw CSI is often converted to DFS features. A model trained on CSI can produce synthetic CSI that appears valid, but after the required transformation is applied, the resulting synthetic DFS is not similar to the real DFS. These errors occur because the generative model is not aware of this subsequent feature transformation. The next step is to solve these problems. Existing generative models directly use generation conditions as synthetic data labels and employ supervised learning for task model training. As we evaluated, it introduced mislabeled synthetic data. On the contrary, our insight is to use a semi-supervised approach that treats synthetic data as unlabeled, selectively incorporating high-quality synthetic samples during training. Our goal is to assign the correct labels to diverse synthetic data. To achieve this, we redesigned the task model architecture and the training losses. In addition to the main task classifier, we introduced another per-class in-layer, out-layer detector. This detector evaluates whether a given sample truly belongs to a specific class. If the detector is highly uncertain about a sample, it likely means the sample is mislabeled and we filtered it out. It can also help reassign a better label to synthetic data when its prediction disagrees with the original condition label. Our detector is trained in two phases. In the first phases, we warm up the model. For real data, we train the model to classify each sample according to its ground truth label. For synthetic data, we enforce decision consistency and prediction sharpness without assuming the label is correct. In the second phase, we iteratively update both the model and the assigned labels. We assign pseudo labels to synthetic samples based on the model's predictions. Then we apply domain-specific processing to the same samples and require the model to give consistent labels. All of these loss components work together towards our goal, making sure the synthetic data we use is both correctly labeled and diverse. We conduct experiments to demonstrate the effectiveness of our approach in improving task performance with high-quality synthetic data. The result shows that our method, the black bar, SynCheck, outperforms all four baselines. The baselines method we compare against include the first one, using only real data. The second one, simply mixing real and synthetic data like previous work did. The third one, filtering synthetic data based on its structure similarity to real data. And the last one, filtering synthetic data using a task model only trained on real data. Our approach achieves consistently better performance than all of these baselines on all models, confirming its advantages in leveraging synthetic data more effectively. We further confirm that the performance gain comes from better synthetic data quality. We re-evaluate the data selected by our system SynCheck and find it has higher affinity and preserved diversity. The strong correlation between data quality and the task performance supports the effectiveness of our quality metrics and SynCheck filtering method. Okay, to conclude, I would like to summarize the key takeaways from our work. The first one is concurrent wireless synthetic data has good diversity but still limited affinity. The reason for limited correctness includes condition transfer failure and domain processing ignorance. Filtering out and relabeling synthetic data can improve affinity and preserve diversity, so in improving task performance. Our full implementation of SynCheck, our evaluation, our benchmark are available at this link. Thank you for your time. I'm now open for questions.
Okay, thanks Bob for great talk. So now we have a couple minutes for Q&A. So you can come to the speaker.
Thanks for your great talk. This is Chenren from HKUST. I'm curious that since your work is dealing with the wireless signals, right?
Yeah.
But from my perspective, I think your work is kind of like a paradigm. I'm curious that if this kind of system can be used to like other modalities such as images or something like that.
Yes, this is a general framework for all modalities like image or voice or other natural language. There are some very specific processing in our training, but you can, but it's an add-on loss component. So if you replace this loss to the other domains loss, you can adapt our frameworks to other modalities.
Okay. Have you tried to do some experiments?
Not yet.
Okay. Thank you.
Okay, thank you for your clear sharing. I'm a student from the Chinese University of Hong Kong. And as your work is focused on task-oriented method to evaluate the quality of the synthetic data, I have some questions that whether you have considered the choice of different parameters or evaluation metrics in the evaluation of the task. And also, the task evaluation method sometimes can be various, like maybe the problem, like maybe by dividing the task set and the training set in different ways, like cross-subject, cross-environment, or just merely mix them together. This kind of things can also affect the final result. Have you ever considered that?
Very good question. For each task, we need to process the data with a special pipeline. If you change the downstream task, you should change the data processing pipeline and train a new model to fill out data or relabel data. So this is a weakness of task-oriented assessment. You should train a new model for a new task.
Yeah, so in your experiment, have you do anything to prove this or to show the generability of your method?
Yeah, we have tried different downstream tasks like classification or regressive. It works well on all different downstream tasks.
Okay. And one more question, only the last question. Okay. Since there are other evaluation methods for the synthetic data, maybe just try to check whether the synthetic data, the data distribution is the same as the original data. I don't know whether your methods can actually meet the conclusion just drawn by these methods. I don't know whether you have some result to show that. Maybe I use another traditional methods and provide a conclusion that, okay, this data is good. And your methods also provide a conclusion this is good, and they just meet with each other. Don't contradict each other.
I try to catch your question.
Okay.
What your question is that the synthetic data and if the synthetic data and the real world data are in the same distribution,
yeah.
We cannot distinguish them, which one is synthetic data, which one is real data. Is this your question?
Not that. I'm only focusing on the evaluation. Since, because we wanted to just test whether the quality is good, right? Yeah. And there are some traditional methods to do this, and you just propose a new method.
Okay.
I just mean whether you have just do some experiments to show that they are the same results.
Got it.
Like this.
Got it. We have some mathematical proof in our paper to show our method is the best method to distinguish the to evaluate the distribution similarity between synthetic data and real-world data. And we take experiments to evaluate different methods, different metrics to evaluate the synthetic data quality, and the results shows our method is the best.
Okay, thank you.
Hi, thank you for the great talk. This is Shiming from Hong Kong PolyU. And you have mentioned that your methods that we first train with the synthetic data and then test with the real and then reverse this process. It makes a lot of sense. And my question is, after we get this difference and the two-step evaluation process, how can we exactly pick up which data in the data set is misgenerated? And after we have picked up this data, we just simply drop them, or is it possible that we can leverage their information to update and refine the data generation framework? Thank you.
Okay, a good question. I think there are two questions. The first one is we propose some metrics to evaluate the synthetic data quality. Yeah, it's a distribution. Yeah, this is a distribution level metric, not a simple level metric. You can use it to evaluate, like, for example, how good is 10,000 data samples, but you cannot use the metric to evaluate a single sample. Yeah, but this is a good indicator. This is already a good indicator. And the second problem is that can we reuse some? Maybe they are labeled as bad data, but there are still some useful information in it, and we want to extract them and reuse it. Yes, in our paper we do two processing on the synthetic data. The first one is we try to filter out the bad data. The second one is we try to relabel some not good but not bad data to a better label to use it in the following downstream tasks.
Thank you for your answer.
Okay, thanks again for our presenter for the great talk and also the insightful discussion with our audience. So now let's move on to our next presentation.